My name is MyoungGon Kim, and I'm the first author from Korea University. I'm going to present our work, EllipssianNet. EllipssianNet estimates 2D Gaussians that match the RGB frequency of the input image. The 2D Gaussians are converted into 3D Gaussians and initialized in 3D Gaussian Splatting framework. The 3D Gaussians are further optimized. For supervised training of EllipssianNet, we created a synthetic dataset using Voronoi diagrams. For this, a Voronoi diagram composed of convex polygons is produced by randomly placing seed points. Each polygon is assigned a random color, which often makes adjacent polygons share the same color. In this case, blue and red polygons become concave. This mixture of convex and concave polygons is taken as the RGB image. The center map encodes the likelihood of each pixel being a convex polygon's centroid. In the covariance map, each pixel is assigned the covariance matrix of the polygon it belongs to. For example, look at this polygon. In this polygon, we compute a covariance matrix using the centroid, the yellow dot, and the boundary pixel centers, the red dots. The computed covariance matrix is visualized as a green ellipse and assigned at the centroid pixel. The covariance matrix at the non-centroid pixel is also computed and visualized. After every pixel is assigned its own covariance matrix, the covariance map is created. Each pixel of the gradient map stores the distance to the nearest polygon boundary. To bridge the domain gap with real-world images, the number of polygons in the Voronoi diagram is varied, and a clustering approach was used to reflect non-uniform object distributions in real world. EllipssianNet follows an encoder-decoder scheme. A ResNet backbone extracts features which are decoded to produce the gradient map. This auxiliary output is used to predict the final outputs, center map and covariance map. Local maxima are extracted from the center map, and the corresponding covariance matrices are sampled from the covariance map. After removing overlapping ellipses, colors are sampled from the RGB image at the surviving local maxima, and combined with the ellipses to define the 2D Gaussians. Results show that EllipssianNet achieves successful cross-domain generalization. EllipssianNet makes a good initialization of 2D Gaussians. We demonstrate the effectiveness of EllipssianNet through two applications. In the first application, Gaussian image, it achieves higher rendering quality with same number of parameters. In our implementation, the input image is divided into 4x4 patches, and EllipssianNet is applied to each patch. The resulting Gaussians are aggregated for initialization and optimization. For comparison, we considered three baseline conditions to isolate the effect of EllipssianNet. Our method begins with higher rendering quality and converges faster. The fast inference of EllipssianNet enables integration into real-time systems such as SLAM. Tracking thread utilizes Droid SLAM to estimate the camera pose and depth map for each keyframe. In sampling thread, EllipssianNet infers 2D Gaussians and lifts them to 3D using the camera pose and depth map. In mapping thread, the 3D Gaussians are integrated and optimized. This video presents a demo run on the replica Office 0 at its original speed. EllipssianNet samples Gaussians at high speed. We compare our method with four baselines. For MonoGS, PhotoSlam, and SplatSlam, rendering quality is evaluated on known keyframes. Ours shows the highest rendering quality. For on-the-fly novel view synthesis, evaluation is conducted on keyframes, since it does not support non-keyframe rendering. Overall, our method demonstrates robust reconstruction. We introduced EllipssianNet, an image-guided framework that directly predicts 2D Gaussians from RGB inputs. We demonstrate two applications, Gaussian-based image representation and real-time monocular SLAM. The code and trained weight are available at GitHub. Thank you for listening.